So, random variables, lecture 3.5. Probabilities are useful even when they do not deal strictly with events. It often occurs that we measure something that has randomness associated with it. We use random variables to represent these measurements. A random variable, x, which maps the sample space to a real number, is a function that maps an outcome, omega, from the sample space, omega, to a real number, x, in the reals, as shown in figure 3.2. So we've got our sample space, there's an outcome, omega. We assign to it a variable, little x. The random variable is the mapping to that assigned random variable, assigned value of the random variable. And the value we usually denote with lowercase, and then with the map we'll usually use the uppercase. A discrete random variable k is one that takes on discrete values. Okay, so a continuous random variable, x, is one that takes on continuous values. So we can have either continuous random variables or discrete random variables. Let's do an example with dice. Roll 2 unbiased dice. Let k be a random variable representing the sum of the two. Let p of k be the probability of the result k. Okay? Plot and interpret p of k. So, do you think this is going to be a random variable that takes on discrete values or continuous values? Discrete, right? That sum is going to be, six-sided die, 1 through 6. We don't have quantum die going on here. So, quantum dice. Great. So, let's do this plot. So the outcomes, what's the lowest one that we can get? 2. Yeah, so this is going to be a plot from 2 to what? 12, yeah. So let's see. My ability to draw a straight line is much inhibited right now due to a strange thing going on in the software. So let's draw some axes. And let's let p of k be here. And let's let k, the little individual outcome, be here. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This was 10. Okay, so let's get another stroke here. So plotting this here, we've got the probabilities being, so what's the probability of getting a sum of 2? So we get 1, but how many, so it's 1/6 times 1/6, right? So 1/36? So this is 1/36. And then 3 is 1/8. And probability of getting a 4 is 1/12. 1/18th. Yeah, you're right. I couldn't read my writing. And then 5 is 1/9. And a 6 is 5/36. And a 7 is the peak, and that's 1/6. And then we're going to have a symmetrical falling, right? There are more ways to get 7 than any other sum. Okay. So what we've just drawn has a name. It's called the probability mass function. This is a probability mass function. So this is like underlined or italics, okay? Or sometimes we just say PMF. It tells us the probability a given sum will occur. Great. Talk more about probability mass functions in the next lecture. Okay. Another example is the Johnson-Nyquist noise example. So a resistor at non-zero temperature without any applied voltage exhibits an interesting phenomenon. Its voltage randomly fluctuates. This is called Johnson-Nyquist noise and is a result of thermal excitation of charge characters, typically electrons. For a given resistor and measurement system, let the probability density function, F sub V, of the voltage V across an unrealistically hot resistor be FV of the voltage equals this exponential function. Plot and interpret the meaning of this function. So, do you guys know what this curve will look like? Zero, 1, 2, 3. And then we've got our vertical axis here. Okay. Oops. Okay, so this is what we'll call a bell-shaped curve. That asymptotically approaches zero. It's symmetric, despite all attempts for me to draw it otherwise. Very poorly drawn bell-shaped curve. So, and this is the voltage here, right? And this is the f sub v, the probability density function. Okay. Now, the probability density function, also abbreviated as PDF, probability density function, must be integrated to find probability. So it's continuous. So, as we'll see, it doesn't have a lot of meaning at a given value. So the probability that a voltage is going to take on the value 1 volt is actually how much? It's the probability that you're going to get exactly 1 volt in this resistor randomly. That's going to be it being less than or equal to plus or minus 1 volt. Yeah. But what is it for exactly 1 volt? 0. Yeah. You have to integrate over some non-zero section of this to find out. So you can find out the probability that it lies under this curve in some region, but the value of the probability density function at a given point is not the probability of it taking on that point. Okay. All right. The probability of a probability of randomly measured variable will be between 2 voltages as the integral across that interval. Note that a resistor would need to be extremely hot to have such a large thermal noise. In the next lecture, we consider more probability density functions. So this would be, I mean, if your resistor was just chilling there on the benchtop and you just put probes across it, you wouldn't really expect it to have a pretty good probability of just like fluctuating up to like a volt, right? And that would be crazy big. So this is a very, very hot resistor. I just gave it scaling that didn't matter. Probably should have done like room temperature or something. And they were just really small numbers and we didn't want to deal with that. Okay. So we're going to get more into PDFs in a moment. But see how for a discrete random variable, the probability mass function, the probability of getting a 5 is 1/9, right? It's the value of the PMF. Whereas with a PDF, you have to integrate over an interval to get a probability.
If it's continuous, we cannot get a point probability.
Correct. So here, the sum of all these probabilities has to equal what? 1. The sum of these probabilities, there's no sum of, I mean, there'd be infinity if you were to sum up all these probabilities. Instead, you would integrate over the entire thing. What is the integral of the entire function equal to? 1. Okay, so if you integrate over the entire thing, it has to be 1. Okay. The voltage never comes out to be banana. Okay? It's always going to be somewhere in there. So, all right. So that's random variables.